so far. Or alpha is the supremum. I always misspell these, I'm pretty sure it's right. Of E. Or we write alpha equals sup E. Sup for supremum. Or we write. Okay, here we go. So all the things is there's the least upper bound, the idea of the smallest upper bound. The supremum of E, same word, just fancy. Okay? And then we write alpha is sup E. So something I could ask you is find the sup of this set. Oh, and sup, not sup. This word is older than the 90s. Just so you know. But, so we, okay. So I have a question. Like I said before, we can do everything for the lower bounds. What do you think we're going to call the best lower bound in a sense? So just like there's least upper bound, there's greatest lower bound. So how do you define that? You define this, it has to be a lower bound, and anything bigger than x is not a lower bound. Right? But you understand. So just like before, let's say beta, so if beta is the greatest lower bound, if beta is the, see this is how I'm horrible with English, lower bound, or beta is the infimum, and we write this as beta is equal to, so I'm not going to define it, but you guys, again, board space, but you see the difference. If I'm saying beta is the infimum or the greatest lower bound, it is an upper bound for, it's a lower bound for E that's such that anything bigger than it is not an upper bound, is not a lower bound. Does that make sense? You switch this inequality and you switch this word for low. So maybe if you want to, let me put it in here. Lower, we put x greater than alpha. Okay, so but we say beta is the infimum of the INF, inf E. Okay? So this is the equivalent for the lower bound. These things, you're going to use them a lot because they make proofs so much easier. But, so I'm going to make a quick remark. The truck goes away. So this isn't going to make sense, so let's start proving things in about 5 minutes. But these definitions are usually used in the negative. So what I mean by this, and you're going to see it in a second. Usually we don't say, oh, this is the least upper bound. We don't usually use, this is the least upper bound, so it has these properties. When you use it in a proof, what you use is specifically this thing. You use, oh, this is less than the least upper bound, so it's not an upper bound. Does that make sense? And you'll see, I'll do it I think 2 or 3 times today, so, and I'll point it out as I go. Because, like that's, I mean, I'm telling you, I've written tons of analysis proofs in my day. I had to take a prelim that involved real analysis. When I took that prelim, I think I used, there's this soup and then you'll learn something called the limb soup. We'll define that when we do sequences. But both of those are generally used like, you go like, well, this is something smaller, so this is not the limb soup, and this is what happens. And there's some consequence of not being the supremum, not being the infimum. Does that make sense? So, and that's how you usually do use them. You prove something is not the supremum, something is not the infimum, and then you use the opposite of this stuff. And I'll show you when I use it in a second. Okay, cool. So let's do a couple of examples again. And yeah, and if you notice number 2 on your worksheet, we'll get there in a second. It's a pretty cool exercise. It's all about this. So, okay, let's do a couple of examples. So let's start with, again, A and B from before. Does A have a supremum in Q? Why not? What's that? Well, it has no, well, what?
Largest.
It has no largest element, right? A doesn't have a largest element, but that's not enough. For instance, okay, let's do an easier example. Let's call this example. What comes before A? Say 0 comes before A. Let's just do an easy example. Here's a perfectly good set. Let's say an R. I know, again, we don't know what R is, but let's pretend we do. What's the supremum of this? Or, yeah, what's the supremum of this set? What's the infimum? 1 is the infimum, 2 is the supremum, right? Again, when I defined everything, there's a greater than or equal to for being a lower bound or an upper bound, right? So 1 is the infimum, 2 is the supremum. So they're in there. But I was going to ask this next, but we'll do it right now. Does the infimum, does the supremum have to be in E? No. Right? The infimum does not have to be in E. In fact, can you guys give me a set where the sup and the inf are not in the set? Perfect. Or how about this guy? This guy has the same supremum, the same infimum. Yeah? 1 and 2, but they're not in the set. So it's not enough to say it doesn't have a maximal element. Okay? But you're close. So you're right, A doesn't have a maximal element, but what else happens? So, God, I'm running out of Roman numeral. A does not have a maximal element. So the answer is no, but that's only half the story. But what else is happening? Well, as we said before, yeah.
Sorry, you were just going to say B doesn't have a minimum.
Right, and since B, we already kind of said B was the set of upper bounds for A. B doesn't have a minimal element either. So there's nothing in the set that's maximal. There's also nothing in the set of upper bounds that's minimal. That's actually why I went through that terrible proof yesterday first thing. So I could say, look at this, we already did it. But A doesn't have it, and also we have to remember B, neither does B. And no, I shouldn't say that. B does not have a minimal element. But the point is, with those two things together, you know together they make the entire positive rational numbers. So there just can't be they can't have a supremum. Similarly, B can't have an infimum, yeah.
Except for 2, right?
What?
Except for 2, right?
Well, 2 is not a maximal element. Remember, these are all the numbers that are technically less than root 2. Remember, their square is less than 2.
I'm saying you use the A and B do not contain 2, right?
They do, because 2 squared is bigger than 2. Let me remind you, A we defined again was being the rational numbers such that R squared, they're positive and R squared is less than 2. And B is R squared is bigger than 2. So 2 is, in fact, every positive rational number is in one of these two sets. But this set does not have any supremum, and that's going to be the big deal. That's why the reals are so cool, and you'll see in a second. You guys want an example that's tougher to see if you guys are? Well, I'll save it. I'll give one more definition, then we'll do another example. Maybe I'll define the reals and do that other example. I have a nice example that I think is tougher, and just to see if you guys are savvy with your old calculus math stuff. Actually, technically pre-calculus. Okay. Yeah, let me give one more definition. I'll give a thing, and then we'll talk about the reals really fast. So the last definition, and this is actually a really good definition, and I don't know why I keep erasing let S be an ordered set, because that's the first thing I write. Let S be an ordered set. We say S has the least upper bound property. The least upper bound property if for all subsets of S such that all subsets E such that E is bounded above, sup